Okay, let's jump into number 1 on this practice exam for exam 3. So number 1 is a multi-part problem that says fill in the circle for the correct answers for each question. There can be more than one correct answer for a question, and no justifications are needed on any of the questions. So we'll start with part A, which says here for a closed constant mass system undergoing a reversible process, which of the following is or are always correct? So we need to choose from this list which of these are always correct for the circumstances that they've provided. A closed constant mass system undergoing a reversible process. So this question is testing our knowledge of entropy, and we can tell because they're talking about a reversible process, which is something that we see when entropy comes up. And the reversible process is one where the entropy generation, sigma gen, is equal to 0. So if there's no entropy produced during our process, then we have a reversible process. And so this term also shows up in our second law entropy balance equation. So what we can do is we can look at that equation, simplify it down for a closed constant mass system, and then apply each of these conditions to it, isentropic, adiabatic, no entropy generation, and see if this term is always going to go to 0. So let's look at our second law equation down in the equation sheet. It shows up right here in the differential form. And so we can simplify it a little bit. Remember that we have a closed constant mass system, so both of these m dot terms are going to go to 0 because there's no mass coming into the system and no mass leaving the system. So these whole terms cancel out here, and we're left with these three terms: our ds dt term, which is our change in entropy, our q dot term, which is our heat transfer across the boundary, and our sigma dot term, which is our entropy generation term. So if we integrate each of these terms, we can get to a version that we like to work with a closed system, and I'll write that version up above, but basically the ddt goes away and the dots are going to go away, and so we are going to get a form that looks like this. Delta S is equal to Q over the temperature at the boundary, and I'll just ignore the summation for now so we can just focus on the terms, but there would usually be a summation there. And then a sigma gen. And so this is our term that we know needs to be 0 for a reversible process. So if we look at each of these options and apply them to this equation, we can see, will this term always be equal to 0? Always. So first off, isentropic process is one where our change in entropy, our delta S, is equal to 0. That's our definition of isentropic. So in this second law equation here, that means our delta S is going to be 0. But, so we could have a case where the heat transfer is also 0 and our sigma gen term is equal to 0, right? Everything is equal to 0. And in that case, we would have a reversible process if this term is 0. But we can also have a case where our delta S is 0, but this sigma gen term is still positive and just the heat transfer term is negative and it cancels it out. So that's a case where we do have an isentropic process because delta S is equal to 0, but we still have some entropy generation because this term here is positive. So whenever we have a positive term for this sigma gen, then we know that it is an irreversible process because sigma gen is not equal to 0 like it should be for a reversible process. So we are not going to select isentropic process because we could still have a case where sigma gen is positive. Next is adiabatic, and it's kind of a similar line of thought. So adiabatic means that our heat transfer, in this case, is going to be equal to 0. And, in a similar fashion, we could have a case where our heat transfer term is 0, and also our other terms are 0, everything is 0. This would be a reversible process because sigma gen is equal to 0. But we could also have a case where our heat transfer term is 0, but we still have a positive sigma gen term, and then our delta S is just positive. So this is an adiabatic case, but again, it's still a positive sigma gen, so we have an irreversible process. So we are also not going to select adiabatic. And the last one is entropy, no entropy generation, which means exactly what we want it to mean. Sigma gen is equal to 0, like we see we have for a reversible process. So no entropy generation just means that this term goes to 0, and then we don't care about what's going on with the other two terms, because for reversible, all we need is just this sigma gen term equal to 0. So we are going to select no entropy generation. And then we're not going to select none of these because we do have one of them here, obviously, so that doesn't make sense. So this is going to be our final answer. Only no entropy generation. Part B of this problem says, for flow of an ideal gas through a constant diameter, horizontal, no work, and adiabatic duct under steady conditions with P1 at the inlet greater than P2 at the exit, the change in entropy S2 minus S1 is always positive, negative, 0, or cannot determine. So there's probably a few different ways that you can think about this problem and rationalize it to get an answer, but I'm going to take you through the way that makes the most sense to me. Again, for these multiple choice questions, you want to try to move through them as quickly as you can and not waste a ton of time, but I'll show you the proof based on the fundamental laws that makes the most sense to me to get to the answer here. So we have a duct like I've drawn out here, and they tell us we'll have some mass flow going through, some flow of an ideal gas. I'll just draw it going from left to right. We'll call that m dot. And we have some pressure at the inlet, P1, that's greater than the pressure at the exit. So we have some high pressure region over here and a lower pressure at the exit here, like to tell us. And we can go through this problem and see what these keywords mean in terms of assumptions that we can make, and then use those assumptions to apply them to the fundamental laws and get to an answer about this change in entropy. So first it tells us that we have a constant diameter duct, which means that the area at the inlet is going to be equal to the area at the exit. So it's not like a device like a nozzle where we have a contraction, a change in area, or a diffuser where we have an expansion. In this case, we just have a constant diameter. And what that really means is that we're not going to have to worry about any changes in velocity or changes in kinetic energy. You know, like for a nozzle, we have an increase in kinetic energy as we speed up the flow going through. But in this case, it's just going to be a constant velocity and therefore a constant kinetic energy. So I'm going to say that our changes in kinetic energy are equal to 0 because we have a constant diameter. Horizontal means that we don't have to worry about any changes in potential energy because there's no changes in height of the fluid or anything like that. There's just a constant potential energy the whole time. No work obviously means that our work term is going to be equal to 0, and then adiabatic means that our heat transfer term, Q, is going to be equal to 0. And we also see that this is happening under steady conditions. So under steady conditions, any time derivatives, any ddt is going to be equal to 0. We don't have any time dependency. So we talked about pressure as well. And we can take these assumptions and just apply them to our fundamental laws. So let's go down to the equation sheet and do that. So we can start just with conservation of mass. I mean, it's a bit intuitive, but what it tells us is that the change in mass over time, dm dt, is going to be equal to 0 because we have a steady state case. And that just tells us that our m dot in is going to be equal to m dot out. That's probably pretty easy to see just from the drawing, but this is what we get. And we can take that and use it in our first law equation here. So again, our change in energy is going to be equal to 0 because this is happening at steady state. And then we said that we're going to neglect any changes in kinetic energy, neglect any changes in potential energy. And we also have an adiabatic case where our heat transfer is 0 and a no work case where our work is equal to 0. So we also see that m dot in is going to be equal to m dot out, and so these terms can cancel out. And the only two terms that we have left are our h in, our enthalpy in, and our enthalpy out. And so what this says is just that h in, which is h1 in this case, minus h2 is equal to 0. Or basically dH or delta H is equal to 0 because enthalpy isn't changing throughout this process. So we're able to get here from our fundamental laws And we can take this now and apply it into our models section for our ideal gases. So we have our models here, and we know that we can use these top two rows for ideal gas. This one is for isentropic ideal gas cases, but we'll just focus on this top two rows right here. And one thing that pops out immediately is that dH equals Cp dt for an ideal gas, but we just said that dH is equal to 0. So we also see that dt is equal to 0. Temperature isn't changing in this case. So that's useful because we have other relationships for entropy right here and right here. And then we want to find this ds, this delta S basically. And they give us information about the pressure, so we have information about the changes in pressure from state 1 to state 2. So we can use this relationship right here because we just learned that dt is equal to 0. So we're just left with ds is equal to minus r times dp over p. So we can just integrate these terms right here. And if we integrate them, we are left with the form, I'll write it up here, delta S equals negative R times the natural log of P2 over P1. So I'm going to take this equation up to our problem because this is what we can use to get our final rational answer for delta S. So we get delta S, or we can just write S2 minus S1 is equal to negative R times the natural log of P2 over P1. But we know that P1 is greater than P2. So if P1 is greater than P2, then this term is going to be in between 0 and 1. Or basically just less than 1. Hopefully that makes some sense. But if it's less than 1, then what that means is this is going to be this natural log of this term that's less than 1 is going to be negative. So this whole term here is going to be negative. And so we have a negative here times a constant times another negative, and that will just give us an answer that is greater than 0. So S2 minus S1 is going to be positive. Hopefully that makes some sense. So this term less than 1 makes this whole term negative times another negative equals a positive. So we see finally that S2 minus S1 is going to be positive here. And so this is just the full explanation of the way that makes the most sense to me based on the assumptions that we can take from the problem statement. But again, try to move through these problems quickly. But I think this is the best way to think about it based on the information that they've given us here. So the final answer is going to be positive. Part C is asking for two different process paths between the same initial and final states. Which of the following must always be the same for both processes? So I think it can be a bit challenging to understand what the problem is asking here, but really what they're getting after is which of these options are path independent. Because they're asking for two different process paths, which of them have the same value for two different paths. So if they have the same value over two different paths, then it doesn't matter what path they take. That is something that we call path independent. So I'm just going to write that out. Really what the problem is asking is which of the options are path independent. So for these options, this is sort of something that you just have to know which of these are path dependent versus path independent. But there is something that we should remember that are always path independent, and that is our state properties. So state properties never depend on path. So they're always path independent. And in this case, we do have some state properties here. We have entropy and energy. So this is asking about changes in them, but changes in state properties are always the same regardless of the path that is taken. So in fact, whenever you see changes in state properties, we'll usually write them, if we're writing them in the differential form, with a d, for an exact differential. So this is something that we would write for a state property because it doesn't depend on the path. Whereas for something like heat transfer, when we write out a differential form of heat transfer, we'll usually write it with this little delta, which means we're taking a path-dependent approach. So the same is true for entropy generation. We would write that out with a delta, and energy is a state property, so we would just write that out with a d for the exact differential for energy. So the answer for this is going to be entropy change and energy change, because these two are state properties, and we know that state properties are always path independent, whereas heat transfer and entropy generation are not. Part D, the final part of this problem, says a rigid tank with one inlet and no outlets initially contains gas at a low pressure. A valve is opened and the tank is adiabatically filled from a supply line until the tank pressure equals the supply line pressure. For each expression, indicate whether it is valid or not for the system and process. So they want us to look at each of these equations that they provided and see if those equations are valid or not. So I've sketched out this scenario. On the right here, we have our tank, which is rigid, and then this valve here. So initially the pressure in the tank is lower, and when this valve is opened, mass is allowed to flow through from this supply line at a higher pressure into the tank until the pressure equalizes, and this pressure in the tank becomes equal to the pressure of the supply line. So that's what's happening with our process. And basically, it looks like these equations here, this first one is some version of first law, energy balance, and then these second two are some version of our second law, entropy balance. So we can just look at this problem statement and figure out what assumptions we need to make based on this process. And then we can just go into our equation sheet and simplify out first and second law ourselves and see what version of the equation we get once we simplify. So we can just look at our problem statement and see what assumptions we need to make. The first thing is that it says this tank is rigid, which means that our work term is going to be equal to 0 because the walls of this tank are fixed. They're not able to move, so we're not going to have any boundary work, and we don't have any other types of work, so our work is going to be equal to 0. One inlet and no outlets, so we see that in our schematic. We only have an inlet and no outlets. And then we also see here that we are filling this tank adiabatically, which means that our heat transfer term Q is going to be equal to 0 as well. So that's kind of all we need in order to simplify here. We can make some other assumptions down in the equation, but let's go down to the equation sheet and we'll look at our first law and our second law equations. So starting here with our first law equation, we know that we have no outlets, so this whole term is going to go to 0 because there's no mass coming out of the system, only our one inlet. We can also just neglect any changes in kinetic and potential energy, so those terms would go to 0 because we're not given any information about any velocity or any potential energy of the fluid. And then, like we said, our heat transfer term is going to 0 because this is happening adiabatically, and our work term is going to 0 because we have a rigid tank. So all that's left is this m dot h in term and our dE dt. So if we just integrate both of these terms, what we get is, and we need to be careful because we have a transient analysis here, so we have to worry about the total energy of the system and the total mass of the system. Hopefully you've had some practice with this, but I'll write it out up here. What we should get when we integrate this dE dt term is m2u2 minus m1u1, right? Because our total energy, E, and we're neglecting changes in kinetic and potential energy here, so we're not going to include those, but that's equal to our total internal energy, which is equal to our mass times our specific internal energy. But the mass here is changing from state 1 to state 2. So we'll initially have some mass m1 inside, but then once mass starts flowing in here, then we have a new mass m2. So this is what we should get from this integration here. And then the other side, we're just integrating this m dot h term. So it's just going to be equal to the total mass in times the enthalpy in, which would be the enthalpy at the inlet, or basically the enthalpy of the supply line here. So this is what I think we should get for our first law equation. But we see here they forgot to take out this heat transfer term, and so this is going to be wrong because we have this version of the equation, so this part is not valid. And now we can look at our second law entropy balance, which is right here. Again, simplifying in a similar manner, we don't have any outlets, so this term goes to 0. And again, this is adiabatic, so this heat transfer term is also going to go to 0. And this is the version that we get. Again, we can just integrate all of the terms here. So we're going to integrate ds dt, and it's going to be a similar thing here where our total entropy is going to be equal to mass times specific entropy. And so once we integrate this term, we will get m2 times s2 minus m1 times s1. This is the result of this integration here. And that should just be equal to m in, once we integrate this m dot term, it just goes to the total mass, m in times s in, plus sigma gen. So we integrate this term, and the dot just goes away down here, and we're left with the total entropy generation. So this is what we should get for our version of second law, but that doesn't match either of these equations here, because this one has a negative sign here and a negative sign here, so both of these signs are wrong because this should be positive and this should be positive as well. And then this one, again, it's a negative sign here, but it doesn't have that plus sigma gen term here. And so this is the version that we think should be right, and so both of these would not be valid as well. So this is our final answer. None of these equations are valid.